The first equation that we're going to start with is pressure. Pressure is defined as force divided by area. So force is measured in newtons, and area, if you take the area of a rectangle, it's the length times width, and it has the units square meters, or at least that's the standard unit. It turns out that 1 Pascal is equal to 1 Newton per square meter. And so Pascal is like the standard unit of pressure. But in chemistry, you tend to use units of ATM. 1 ATM is equal to 760 units of torr, which is equal to 760 millimeters of mercury, and that's equal to 101.3 kilopascals, which is 101,300 pascals. Now, another equation that you'll encounter in chemistry is the ideal gas law equation. PV is equal to nRT. P is the pressure of the gas, V is the volume, N is the moles, R is the gas constant, which is equal to 0.08206. Now you need to pay attention to the units here. It's liters times ATM over moles times Kelvin. So whenever you have an R in the equation, notice that if you use the 0.08206 value, notice that you have the units liters, which means that the volume has to be in liters. And notice that we also have ATM. So pressure has to be ATM. It can't be in torr. It can't be in millimeters of mercury. You need to convert it to ATM. Now N, of course, is going to be in moles. So that's not going to change. And the temperature has to be Kelvin. For all of the gas law equations, make sure the temperature is in Kelvin. Now, to convert the temperature to Kelvin, it's the Celsius temperature plus 273. You can make it 273.15 if you want, but adding 273 will suffice. And if for some reason you're given the Fahrenheit temperature, you can convert it to Celsius using this equation. The Fahrenheit temperature is 1.8 times the Celsius temperature plus 32. Now, you can also use the R value 8.3145, but this has the units joules per mole per Kelvin. Now you can make this work, but pressure has to be in kilopascals if you choose to use this R value. But that's up to you. Personally, I prefer to use the 0.08206 because ATM is a common unit of pressure in chemistry. So now going back to the ideal gas law equation, there are some other equations that you can get from it. So let's solve for R. If we divide both sides by NT, we'll get that R is equal to PV over NT. So let's put a 1. Let's say this is P1, V1, N1, T1. Well, R is also equal to P2, V2 over N2, T2. So here we get the combined gas law equation, which using that equation we can get a lot of other equations. So let's start again with the combined gas law, which we said was P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Now, for Boyles Law, Boyles Law describes the relationship between pressure and volume. So therefore, he keeps the temperature and the moles constant, so we can eliminate that from the combined gas law equation. So Boyles Law, the equation that is associated with it, it's P1 V1, which is equal to P2 V2. Now, if you were to make a plot between the volume and the pressure, it's going to look like this. So as the volume of the gas increases, the pressure decreases. So the pressure and the volume, they have an inverse relationship. So if you double the volume of the container, the pressure will be reduced by half. if you triple the volume, the pressure will reduce by a factor of 3. So let's say if the volume increased from 100 milliliters to 300 milliliters, the pressure will decrease, let's say from 12 atmospheres, it's going to decrease by a factor of 3 to 4 atmospheres. So if you multiply the volume by a factor of 3, the pressure will decrease by a factor of 3. And so they're inversely proportional. So if you want to think about it conceptually, imagine if you have a container, and let's say it's not a rigid container. This container can expand or contract. And so here we have a few gas molecules. And as these gas molecules collide with each other, they're colliding with the wall. Anytime a gas molecule collides with the wall, it exerts a force. And as we've seen, pressure is force over area. So all of these collisions, all these forces that are being applied to the walls of the container, they exert a pressure. And so the more collisions that you have, the greater the pressure will be. So let's say if we increase the volume of the container, what's going to happen? Think of terms of the number of collisions. So we could see that the gas molecules have more space. They have more room to move around. So as we increase the volume of the container, will the number of collisions increase or decrease? So as you increase the volume, the gas molecules, because they have more space, the number of collisions will decrease. And so because they're colliding with the walls of the container less frequently, the pressure will reduce, or will be reduced as well. It's going to go down. And so that's Boyles Law, the relationship between volume and pressure. Now going back to the combined gas law equation, we're going to consider another relationship. And this is for Charles' law. So Charles' law shows the relationship between volume and temperature. Therefore, pressure is constant and moles is constant. So we get the equation V1 over T1 is equal to V2 over T2. So as the temperature of a gas increases, the volume increases. And so his law, he plots temperature on the x-axis and volume on the y-axis. And these two, they increase proportionally. So we have a direct linear relationship. So let's say if the temperature of a gas is 300 Kelvin, and let's double the volume, not the volume, but let's double the temperature to 600 Kelvin. So if we double the temperature, and let's say that the volume is currently 2 liters, what's the new volume going to be? Well, because they're directly proportional, they're both going to go up. If you increase the temperature by a factor of 2, the volume will increase by a factor of 2, so it's going to double to 4 liters. Likewise, if you triple the Kelvin temperature, the volume will triple. And make sure you're dealing with the Kelvin temperature. If you double the Celsius temperature, the volume will double. It's not proportional to the Celsius temperature, it's proportional to the Kelvin temperature. By the way, for this equation, V1 can be in milliliters. It doesn't have to be in liters. If V1 is in milliliters, V2 can be in milliliters. If V1 is in liters, V2 can be in liters. V1 can be in milliliters because we don't have the R constant. In the last equation for Boyles Law, where we had P1 V1 equals P2 V2, P1 could be in torr, and if it's in torr, P2 has to be in torr. If P1 is in kilopascals, P2 has to be in kilopascals. It simply has to match. If P1 is in ATM, P2 can be in ATM. However, for the ideal gas law equation, where it's PV equals nRT, because we have the R constant, pressure has to be in ATM, volume has to be in liters. But for the combined gas law, or any equation that comes from it where there's no R value, the unit simply has to match. But however, temperature cannot be in Celsius. It has to be in Kelvin. If you put it in Celsius, it will not work. You will not get the right answer. Now let's start back with the combined gas law equation. The next equation that we're going to talk about, I messed that up. That's supposed to be N1, T1. Okay, here we go. So the next equation is Gay-Lussac's law. And his equation shows the relationship between pressure and temperature. So volume and moles are held constant. So it's going to be P1 over T1, which is equal to P2 over T2. So as you increase the temperature, the pressure of a gas will increase proportionally. And so if you were to plot the temperature on the x-axis and the pressure on the y-axis, you can have a direct linear relationship, just like Charles' law. So if you double the temperature, the pressure will double. If you triple the Kelvin temperature, the pressure will triple as well. And so that's the main idea behind Gay-Lussac's law. Now, if you think about it, let's say if you heat up a gas, how exactly does the pressure go up? Whenever you raise the temperature of a gas, the gas molecules will move faster. They're going to have more kinetic energy. And the reason why we could say that is kinetic energy, or the average kinetic energy of a gas, is equal to 3 over 2 RT, where R is 8.3145 joules per mole per Kelvin for this equation. So as you increase the temperature, the average kinetic energy of the gas goes up. And whenever the kinetic energy of a gas goes up, the gas particles are moving faster. So therefore, the speed of the gas molecules are increasing. And if the speed is increasing, the gas molecules will be colliding with the walls of the container more frequently. So therefore, if the collisions between the gas molecules and the walls of the container will go up, and whenever that goes up, the pressure will go up. It's going to go up as well. So therefore, anytime you increase the temperature, the pressure will go up for any gas. Now let's see if we can come up with a scenario that can help us to combine the effects of Charles' law and Gay-Lussac's law, as well as Boyles' law. So let's think of a balloon. Let's say at this time the outside pressure is 1 atm and the inside pressure is also 1 atm. So whenever you have a pressure, there's a force. The gas molecules outside of this balloon, they exert a force on the surface of the balloon, and the gas molecules on the inside, they exert an outward force. Because the inside and the outside pressure are the same, the internal forces are equivalent to the external forces, so therefore the balloon maintains its shape. But now let's see what's going to happen if we increase the temperature. We know that whenever the temperature goes up, the kinetic energy of the gas goes up. Gas particles, they move faster, the number of collisions increases, and so the pressure goes up. That's the internal pressure. So let's say if we double the Kelvin temperature, so the pressure is going to double. Now what do you think is going to happen if the internal pressure is greater than the external pressure? So in the beginning, the internal pressure was equal to the external pressure, or the outside pressure. And so the volume was constant. But here, the internal pressure is greater than the outside pressure. So what that means is that the forces, the internal forces, are greater than the external forces. So if the forces on the inside exceed the forces on the outside, notice that the blue arrows are larger than the red arrows. What's going to happen? Well, the balloon is going to expand if the inside forces are pushing it outward, and if it's greater than the outside forces, which are trying to compress the balloon. So whenever the internal pressure exceeds the outside pressure, gas expansion occurs. And so, as a result of increasing the internal pressure, the volume of the balloon is going to increase. Now, granted, you need a vessel that is expandable. If you use a rigid container that won't expand, this is not going to happen. But for balloon, when you increase the internal pressure, the volume of the balloon will expand. And so, according to Boyles Law, what happens when the volume goes up? Whenever the volume goes up, we said that the pressure will go down. So right now, the balloon's going to get bigger. And so, as it gets bigger, the gas molecules inside of the balloon, they're going to have more space. And so, because they have more space, they will collide less with the walls of the container. And so, because the collisions will be reduced, the pressure is going to go back to normal. And so, once the internal pressure equals the external pressure, the balloon will no longer expand. It will stop expanding at this point. And so, what we've reached is a state of equilibrium, where the outside forces are equal to the inside forces. And so, expansion will cease to occur. So, as you can see, according to Lukas Law, whenever you increase the temperature, the pressure goes up. And according to Boyles Law, when you increase the volume, the pressure is reduced. But the net effect is consistent with Charles' law, because when the temperature went up, the end result is that the volume went up. First, the pressure increased, and then as the volume increased, the pressure was brought back down. So overall, the pressure is constant. It went up to 2, and it went back down to 1. So the net effect is, as we increase the temperature, the volume of the balloon expanded. It increased, according to Charles' law. Now, there's another law that we need to talk about. So let's rewrite the combined gas law equation. So this law is known as Avogas Law. And of course, whenever you hear Avogadro's name, think of moles. As you know, 1 mole is equal to 6 times 10 to the 23 particles or atoms, molecules, or just stuff in general. So, for Avogadro's law, his law describes the relationship between moles and volume. So therefore, pressure is constant and temperature is constant. So the equation that's left over is V1 over N1 is equal to V2 divided by N2. So, as you increase the moles of the gas inside of a container, the volume is going to increase. Of course, if it's an expandable container. So let's plot moles on the x-axis and volume on the y-axis. So we have another direct linear relationship. So if you double the moles of gas, the volume will double. And a good way to think about it is a balloon. Let's say you have a balloon and we have 1 mole of gas. If you blow more air or more moles of gas or more moles of air into the balloon, what's going to happen? As you blow more air molecules into the balloon, the volume of the balloon is going to expand. You know that. You've seen that happen in real life. Now let's understand how it expands. So, as the moles of gas increases, there's more gas particles inside the balloon. So therefore, if you have more gas particles, you're going to have more collisions with the walls of the container. Or in this case, the inside of the balloon. So as you increase the moles of gas, there's more particles, so more collisions, and therefore, the pressure initially goes up. And when the internal pressure is greater than the outside pressure, the volume of the gas will increase. The gas will begin to expand. And as the gas expands, the pressure will be reduced. So these two will cancel out. The pressure goes up, then it goes back down. So overall, the pressure remains constant at the end of the system, at the end of the change. So the net result is that as you increase the moles of the gas, the volume of the gas will expand due to changes of pressure. The pressure goes up, gas expansion occurs, and the pressure is brought back down to a system of equilibrium. And so as you increase the moles, the volume goes up. Now, if you have a container that is not expandable, let's say if you have a rigid container, If you increase the moles, then the pressure is going to go up. And because the volume won't change, this is not going to happen if you have a rigid container. But for a balloon, if you add more moles of gas, the volume will go up, which is consistent with Avogadro's law. The next thing that you need to know about gases is something called STP. STP stands for standard temperature and pressure. The standard temperature of a gas is 273 Kelvin or 0 degrees Celsius. And the standard pressure is 1 atm, which is the same as 760 torr or 760 millimeters of mercury or 101.3 kilopascals. Now, at STP, it turns out that 1 mole of gas occupies a volume of 22.4 liters. So let's see why that's the case. So go into the equation PV is equal to nRT. So the pressure at STP we said was 1 atm. We're going to solve for volume. The moles, we're going to plug in 1 mole. We're going to see the volume that 1 mole of gas occupies at STP. Now R is a constant, that's 0.08206, and we said the Kelvin temperature at STP is 273. So if you take your calculator and if you multiply the 3 numbers on the right, well, you really don't need the 1, but if you take 273 and multiply by 0.08206, guess what number you're going to get? On the right side, it's going to be 22.4. And on the left side, it's going to be 1 times V, which is just V. So it's 22.4 liters. And so that's the molar volume. So 1 mole of gas at STP occupies a volume of 22.4 liters. Now the next equation we need to talk about is the density of a gas. So density is defined as mass over volume. Now for gases, in chemistry, the mass of the gas is usually in grams and the volume is usually in liters. So the density of a gas is usually reported in grams per liter. But what equation should we use on a practical basis? Let's derive the equation. Let's start from the ideal gas law equation. PV is equal to nRT. Now the first thing you need to keep in mind is that the moles of a gas is equal to the mass divided by molar mass. Now I'm going to use capital M as molar mass. I know sometimes capital M could represent molarity, but for this equation I'm going to use it for molar mass. You could change it to something else that suits whatever variable that you want to use. But for now, lowercase m represents the mass in grams, and capital M is the molar mass in grams per mole. So if you want to see how the unit works, mass is grams over 1, which is just grams. Molar mass is grams over mole. So this is the same as grams divided by grams over mole. Now perhaps you heard of an expression called keep, change, flip. It's a process where you can divide 2 fractions by converting it to multiplication. So you keep the first fraction, change division to multiplication, and then you flip the second fraction. So as you can see, the units grams cancel and you get moles. Or another way you can see this is if you're converting from grams to moles. Let's say if we have 24 grams of carbon. Now the molar mass of carbon, or the atomic mass, if you look at the periodic table, it's 12. It's 12 grams per mole. So what this means that 1 mole of carbon has a mass of 12 grams. And so to get the moles, we need to divide the mass of 24 grams by the molar mass of 12 grams per mole. And so we'll get 2 moles. So therefore, this equation is true. Moles is equal to mass divided by molar mass. So what we're going to do now is we're going to replace the moles, or N, with mass over molar mass. So M over capital M. And now our next step is to multiply both sides by the molar mass. So on the right side, M will cancel. So we now have this equation. PVM is equal to MRT. So pressure in ATM times the volume in liters times the molar mass in grams per mole. So make sure you make a mental note that this is going to be grams per mole. And the mass in grams times R times T. Temperature is in Kelvin. So this equation is going to be useful. I would save this equation. Whenever you have to find the molar mass of a gas, and if you're given the mass in grams, use this. Solve for capital M. Because sometimes you may get a multiple choice problem where they ask you to identify the gas. And your options might be like N2, O2, helium, argon, CO2. And for such a problem, if they give you mass, plug it in, solve for molar mass. And once you have the molar mass, you can look at your answer choices and see which gas has the molar mass or the same molar mass as the answer that you have. So if you need to find the molar mass of a gas, given the grams of the gas, use this equation. Or you can use PV equals nRT, get the moles, and then take the mass divided by the moles. That will give you molar mass as well. So keep in mind, molar mass, if you ever need to find it, it's simply the mass divided by the moles. Take the grams divided by the moles and you should be fine. So now from this equation, what we're going to do is we're going to divide both sides by V. So if we divide by the volume on the left side, the volume cancels. So what we now have is pressure times molar mass is equal to MRT over V. But I'm going to write it as MRT, but I'm going to divide V here. Keep in mind, we said that density is equal to mass divided by volume. So you can replace M over V with density. So here's the equation. Pressure times the molar mass of a gas is equal to density times RT. So in this equation, if you're given the molar mass of the gas, which you can find using the periodic table, you can calculate the density. So let's say if we want to find the density of N2, the molar mass is 14 times 2, which is 28 grams per mole. So if you plug in 28 for M, plug in the pressure, plug in the temperature, and then you'll get the density of a gas. Also, sometimes you might be given the gas density and you need to solve for the molar mass, so you can use this equation as well. But now let's isolate density. Let's divide both sides by RT. So therefore, RT cancels on the right side. And so we get this equation. Density is equal to pressure times molar mass divided by RT. So what is the effect on gas density if you increase the pressure of a gas? Is the density going to go up or is it going to go down? So notice that pressure is in the numerator of this fraction. Whenever you increase the numerator of a fraction, the value of the entire fraction goes up. So as you increase the pressure, the density of the gas will increase. So if you double the pressure, the density will double. If you triple the pressure, the density will triple. Now what about the molar mass of a gas? How would you describe the relationship between gas density and molar mass? Because the molar mass is in the numerator with the pressure, that tells us that as the molar mass of the gas increases, the density will increase as well. So heavy gas molecules will create a sample that's more dense than light gas molecules. It makes sense because keep in mind, density is mass over volume. So if you can increase the mass while keeping the volume constant, the density will increase. And because the volume is in the bottom, whenever you increase the denominator of a fraction, the value of the entire fraction decreases. So if you increase the volume of a gas, the density should therefore decrease. So now let's look at temperature. Let's see how temperature affects gas density. As you increase the Kelvin temperature, if you double it, the density will decrease. Now how is it affected by temperature? Now keep in mind, think about Charles' law. If we have an expandable container, as you increase the temperature, the end result is that the volume will increase, of course, due to changes in pressure, but overall, whenever you increase the temperature, the volume goes up. And as we can see here, if we increase the volume, gas density goes down. So we can see how this relationship is true, and since this one is true, this is true overall. So whenever the temperature of a gas increases, and if the gas expands, the density of the gas will decrease. Now going back to that equation, D is equal to PM over RT. Now let's say if we increase the temperature of a rigid container where the volume is constant, what happens to the gas density? If the volume is constant, then think about Gay-Lussac's law. The pressure is going to increase. So whenever the pressure increases, we said that the density goes up. But if the temperature increases, the density goes down. So therefore, these two, they sort of cancel out, and the density is going to stay the same because the volume is the same. Keep in mind, density is mass over volume. If you increase the temperature, the mass of the gas inside the container is going to be constant because you're not adding more gas molecules, so the mass is constant. And if you have a rigid container, the volume is constant, so therefore the density is constant. So even though the pressure goes up, the temperature goes up as well. So let's say if you increase the pressure to 2, and let's say you keep the molar mass the same, and let's say R is constant. 1 means that it doesn't change, but let's say the temperature doubles. 2 over 2 is 1, so the density stays the same. So whenever you increase the temperature of a gas, and the container is rigid, meaning that the volume won't change, the pressure is going to go up, and so the density will remain constant. That's the other thing you need to understand. Now, if you can increase the pressure by increasing the moles of gas, if you have a rigid container, if you add more moles of gas, the pressure will go up. And because you add more moles of gas, you've increased the mass, even though the volume is the same. And whenever you increase the mass, the density goes up. So that's how pressure is related to density. If you add more moles of gas and you increase the pressure, the mass of the gas goes up, density goes up, and that's how pressure and density are related, if the mass of the gas changes. The other way is if you decrease the volume. If you decrease the volume, the pressure will go up. And therefore, density will increase. So keep in mind, in the last example, we said that if we increase the volume, whenever you increase the denominator of a fraction, the entire value of the fraction goes up. The entire value of the fraction goes down whenever you increase the value of the denominator. So since the value of the fraction goes down, the density goes down whenever you increase the volume. So if you decrease the volume, or if you decrease the denominator of a fraction, the value of the fraction goes up, so density goes up. And we can see that here. If you decrease the volume, according to Boyles Law, pressure goes up, and so the density will go up as well. Now the next thing we need to discuss is Dalton's law of partial pressures. So his law states that the total pressure of a gas is equal to the sum of the partial pressures. So P1 plus P2 plus P3. So let's say if the partial pressure of N2 is 500 torr and the partial pressure of O2 is 100 torr. Actually, let's make that 200 torr. And let's say the partial pressure of argon is 50 torr. So according to Dalton's law of partial pressures, the total pressure is the sum of the partial pressures, so that's 750 torr. So you might be wondering, what is the difference between total pressure and partial pressure? So the partial pressure of N2 is basically the pressure exerted only by N2 molecules. The partial pressure of O2 is the pressure exerted only by oxygen gas molecules. The total pressure is the pressure exerted by all the molecules. So it takes into account the collisions caused by all three of these molecules in the container. Whereas the partial pressure is related to the collisions exerted by a specific molecule or substance in this sample. Now there's something else that you need to know, and that's mole fraction. The mole fraction of substance A is the partial pressure of substance A divided by the total pressure. Also, the mole fraction is the moles of substance A divided by the total moles. Now the sum of the mole fractions of all gases should add up to 1. So let's say if we have argon, nitrogen, and oxygen, the mole fraction for nitrogen plus the mole fraction for argon and the mole fraction for O2 should add up to 1. The mole fraction is basically the decimal form of a mole percent. So you know how you have mass percent and volume percent? Well, you also have mole percent, but the decimal form of mole fraction is mole percent. So let's say if 20% of the gas molecules is oxygen, the mole fraction of oxygen would therefore be 0.20. Now, another thing you need to know is that the partial pressure of a gas is equal to the mole fraction of that gas times the total pressure. Now, the best way to understand how these equations are linked with one another is to use an example. So let's go over a very simple example. So let's say if we have 7 moles of nitrogen gas, 2 moles of argon gas, and 1 mole of oxygen gas. So the total moles is 7 plus 2 plus 1, which is 10. So let's calculate the mole fraction of nitrogen. The mole fraction of nitrogen, we said, is the moles of nitrogen divided by the total moles. So we have 7 moles of N2, and the total moles, 7 plus 2 plus 1 is 10. 7 over 10 is 0.70. So that's the mole fraction for N2. So what this means is that 70% of the molecules in this sample is nitrogen gas. That's what it means. That's what the mole fraction is. And the mole fraction of argon, there's 2 moles of argon out of a total of 10, so that's equal to 0.2. And so what this means is that 20% of the molecules is argon. So if we had 1,000 molecules, we would have 700 molecules being nitrogen, 200 molecules would be argon. Now the mole fraction of O2 is 1 over 10, so basically 0.10 or 10%. So 10% of the molecules would be oxygen. So out of 1,000 molecules, 100 of those molecules is therefore oxygen gas. So now keep in mind, if you want to write these numbers down, feel free, or you can rewind the video and look at these numbers again, because I'm going to clear the page. By the way, going back to this page, notice that if we add the total mole fraction, as you mentioned earlier, it adds up to 1. So if you add 0.70, 0.20, 0.10, the total is 1, because the total percentage is always 100%, and 100% as the decimal is 1. So the sum of all mole fractions is 1. So let's say if you know the mole fraction of nitrogen gas and argon gas, you could find the mole fraction of O2. It's going to be 1 minus the mole fraction of N2 and argon. So now let's say if the total pressure of the gas is 1,000 torr. 1,000 is a nice number. Let's calculate the partial pressure of each gas. Now keep in mind, the partial pressure is the mole fraction times the total pressure. So the partial pressure for nitrogen gas is the mole fraction of N2, which is 0.70 times 1,000. So basically it's 70% of the total pressure. 70% of 1,000 is 700. So that's going to be the partial pressure of N2. Now the partial pressure for O2, it's, I believe we said it was 0.10. So it's going to be 10% of 1,000, which is 100 torr. And the partial pressure for argon, that was 0.20 in the last example. So 20% of 1,000 is 200. And notice if we add the partial pressures, we're going to get the total pressure according to Dalton's law. So 700 plus 1,000 plus 200 is equal to 1,000 torr. So as you can see, everything makes sense. So now you understand the relationship between total pressure and partial pressure and how it's associated with the mole fraction. Now, another equation that you need to know is the root mean square velocity of a gas. But let's derive the equation first. Now keep in mind, we said that the average kinetic energy of a gas is equal to 3 over 2 RT. So the individual kinetic energy of a gas particle might vary. Some gases might be moving fast, others might be moving slow, but the average, if you have a million gas molecules, they're going to average out to a certain number. The average kinetic energy of a gas, the average of billions of molecules, is proportional not to the mass or the velocity or the pressure or anything like that. It's only proportional to the temperature. So if the temperature of a gas is constant, the average kinetic energy of a gas will not be. So if you increase the temperature, the average kinetic energy of the gas will increase. So this is part of the kinetic molecular theory, which states that the average kinetic energy of a gas is directly proportional only to temperature. Now, that's the average of a billion gas particles. But now, what about the kinetic energy of a single particle? Now, that can vary. The kinetic energy of a single molecule, if you go back to physics, it's 1/2 mv squared. So, if you double the mass of just a single particle, the kinetic energy will double. If you double the speed, because it's square, 2 squared is 4, the kinetic energy will quadruple. Because kinetic energy is proportional to mass, but it's directly proportional to the square of the velocity. So if you're looking at a single particle, then yes, the kinetic energy of that single particle is dependent on the mass and the speed. However, if you're looking at the average kinetic energy, it is not dependent on the mass and the speed. It's dependent only on temperature. So make sure you're aware of that difference. Now, if we can combine these two equations, we can use that to get the root mean square velocity of a gas. But you have to be careful with the units, because we can't set them equal to each other right now at this point. R has the units joules per mole per Kelvin. And if you multiply it by the Kelvin temperature, we get the units joules per mole. By the way, for this equation, R is not 0.08206. It's 8.3145 joules per mole. So you can use the 0.08206 number for the equations PV equals nRT, and you can also use it for any equation that's derived from the ideal gas law equation PV equals nRT. So for the equation for gas density, which equals pressure times molar mass over RT, you can use the R value 0.08206, but if you use it, pressure has to be in ATM, and temperature has to be in Kelvin, the molar mass has to be grams per mole, and you're going to get the density in grams per liter. You can also use 0.08206 for the other equation that I told you to save. That was pressure times volume times molar mass equals m, lowercase m, which is mass times R times T. So if you're going to use 0.08206, make sure that the pressure is in ATM, mass is in grams, molar mass is in grams per mole, and then it's going to work. Now, for this equation, R is in joules per mole, and it makes sense because kinetic energy is usually in joules. Now, for this equation, we have mass in kilograms, we have the speed, which is meters per second squared. 1 kilogram times 1 meter per second squared is equal to a joule. However, we don't have moles in this equation, so we need to introduce it. So what we need to do is multiply this equation by 1 over n, because n is in moles, and then we can have the units joules per mole. So the kinetic energy divided by the moles is equal to the average kinetic energy, which has units joules per mole. So moles, I'm going to write it as 1 over n times the kinetic energy of an object, which is 1/2 mv squared. The average kinetic energy we said was 3 over 2 times RT. So if we multiply both sides by 2, we can cancel the fractions. The 2 over here will disappear, and the 2 will disappear as well. Now, what is mass divided by molar mass? Keep in mind, earlier we said that moles is equal to mass over molar mass. So if we multiply both sides by m and at the same time divide both sides by n, notice what we'll get. So on the right side, m is going to cancel, but on the left side, n is going to cancel. So therefore, the molar mass is the mass over the moles, which means that we can replace m over n with big M. Mass divided by moles is molar mass. So now let's replace m over n with molar mass. So we have molar mass on the left side times the velocity squared, and that's equal to 3 RT. So let's divide both sides by m. So on the left, m is going to cancel, so v squared is equal to 3 RT over m. So if we take the square root of both sides, the velocity, or the root mean square velocity of a gas, is equal to the square root of 3 RT over m. Now the speed is usually in meters per second. So for this to work, you have to use the r value, not 0.08206, but 8.3145 joules per mole per Kelvin. The temperature has to be in Kelvin. Now the molar mass is not going to be in grams per mole. It has to be in kilograms per mole, because we use the equation kinetic energy is equal to 1/2 mv squared. And in physics, to get the kinetic energy in joules, the mass has to be not in grams, but in kilograms. So let's go over an example. Let's say if we have the oxygen gas molecule. What's the molar mass of O2 in kilograms per mole? So oxygen has an atomic mass of 16. So 16 times 2 is 32. But that's 32 grams per mole. Whenever you need to go from grams to kilograms, you can simply divide by 1,000. And if you need to go to grams from kilograms, multiply by 1,000. So 32 grams over 1 mole. And we know that there's 1,000 grams per kilogram. Make sure you know your units. 1 kilogram is equal to 1,000 grams. You can see that we need to divide. So 32 divided by 1,000 is 0.032 kilograms per mole. So if you want to get the root mean square velocity, if you want to get the right answer, this is what you need to plug in for the molar mass of oxygen gas. Now, going back to the root mean square velocity equation, let's talk about the relationship between temperature and molar mass and the speed. If you increase the temperature, what's going to be the effect of the speed of the gas? We can see that temperature is on the top of the fraction, so therefore, if you increase the numerator of a fraction, the whole fraction goes up in value. So if you increase the temperature, the velocity of the gas will increase. So at high temperatures, gases, they're moving faster and faster. Now, if you increase the molar mass of a gas, the velocity will decrease. And that makes sense because heavy gas molecules move slower, but light gas molecules move faster. Now, let's say if we increase the Kelvin temperature from 300 to 1200. So we've increased it by a factor of 4. 3 times 4 is 12. What's going to be the effect on the velocity if the initial speed is 100? What's going to be the new speed? Now, notice that the velocity is proportional to the square root of the temperature. That square root is important. So here we have a 4. The square root of 4 is 2. So the velocity is going to increase by a factor of 2. So it's going to double in speed. So if you were to increase the Kelvin temperature by a factor of 9, the velocity will increase by a factor of 3 because the square root of 9 is 3. Now, what if you increase the Kelvin temperature by a factor of 2? If the temperature goes up by 2, the velocity is going to increase by the square root of 2. If you triple the Kelvin temperature by a factor of 3, the velocity will increase by the square root of 3. So, as you can see, the equation has a square root, so that's why. Now, what about the molar mass? Let's make some space. So, let's say if the molar mass increases by a factor of 4. So let's say the molar mass is currently 16 for one particular gas molecule, and for the other gas molecule it's 64. What's going to happen to the velocity? We know that if you increase the molar mass, the velocity goes down. So let's say the velocity was 100 meters per second. If the molar mass increases by a factor of 4, the square root of 4 is 2, the velocity is going to decrease by 2, so we have to divide by 2 since it's decreasing. If it's going to increase, we would multiply. So it's going to be half of what it was, which means it's going to be 50. Now, if you were to increase the molar mass by a factor of 9, the velocity would decrease by a factor of 3, or you have to divide it by 3. So the velocity is inversely proportional to the square root of the molar mass. The next equation that we need to derive is Graham's law of effusion. But I think we should spend some time on discussing the difference between diffusion and effusion. So let's say if you spray a perfume, and so you have the gas particles here. What's going to happen is this gas is going to diffuse everywhere into the room. It's going to spread out in all directions. And so diffusion is the process or the movement of a material from a region of high concentration to a region of low concentration. So that's diffusion. Effusion is the process where a gas, which is in a container, leaves the container through a hole. So if there's a tiny opening in the container, the process where the gas leaves through the container is effusion. Now, granted, the gas is still flowing from a region of high concentration to low concentration. But instead of calling it diffusion, it's effusion if it escapes through a hole in a container. So that's what effusion is. Now, we need to talk about how to derive the equation for Graham's law of effusion. And it turns out that you can find it by using the root mean square velocity equation. So V2 over V1 is going to be equal to the square root of 3RT over M1. So let's assume that temperature is constant. The only thing that's changing is the molar mass, because Graham's law of effusion he connects the rate of effusion to the molar mass of a gas. So assuming temperature is a constant. So if temperature is constant, we can cancel it from the equation. We can also cancel 3R. So therefore, what we have is the square root of 1 over M1 is equal to the square root of 1 over M2, and that's V2 over V1. By the way, the square root of 2 over 3 is the same as the square root of 2 divided by the square root of 3. So we can write this as a single radical. So we can say that this is the square root 1 over M1 divided by 1 over M2. So now let's focus on that fraction. 1 over M1 divided by 1 over M2. So this is the same as 1 over M1 divided by 1 over M2. So using the principle keep, change, flip, we're going to keep the first fraction, change division to multiplication, and then we're going to flip the second fraction. So therefore, what we have is this fraction is equal to m2 over m1. So therefore, v2 over v1, which was equal to the square root of 1 over m1 divided by 1 over m2, that's equal to the square root of m2 over m1. Now, velocity is a rate. In physics, there's the equation distance is equal to speed multiplied by the time. Now, granted, velocity and speed have the same magnitude. Velocity is just speed with direction. Now, this equation is also similar to this one. Distance is equal to rate times time. So what you need to know is velocity is a rate. So therefore, we can replace this with a rate, or a rate of effusion. Gas particles with a high velocity have a high rate of effusion. So now we can come up with Graham's law of effusion, which is R2 divided by R1 is equal to the square root of m1 over m2. So that's Graham's law of effusion. The rate of effusion is inversely related to the square root of the molar mass of a gas. And rate and velocity are proportional. Velocity is a rate. So whenever the molar mass of a gas increases, we know that the velocity decreases. So therefore, as the molar mass of a gas increases, the rate of effusion decreases. So let's compare two gases. Let's look at, let's see, helium gas and oxygen gas. Helium has an atomic mass of 4 grams per mole, and for oxygen is 32. So as you go from helium to oxygen, the molar mass, actually instead of using helium, let's use hydrogen gas. The molar mass of hydrogen gas is 2, and for oxygen is 32. So as you go from hydrogen to oxygen, the molar mass increases by a factor of 16. Now keep in mind, the rate of effusion is inversely related to the square root of the molar mass, because as you look at the equation, for the rate, the 2 is on top, but for the molar mass, the 2 is on the bottom. So that tells you that they're inversely related. So let's say that the rate of effusion for hydrogen, let's say it's 100. What is the rate of effusion for O2? So as the molar mass goes up, the rate goes down. And keep in mind, there's a square root involved. So if you take the square root of 16, what do you get? The square root of 16 is 4. And because the molar mass increased, we know the rate has to go down. So we're going to divide by 4 and not multiply by 4. So 100 divided by 4 is 25. And so if the rate of effusion of hydrogen is 100, the rate of effusion for oxygen is going to be 4 times less. It's going to be 25, because oxygen is 16 times heavier than hydrogen. So now at this point, we've covered all of the important equations for gas laws, at least the most common ones. But there is one that I do want to mention, and it's gas density at STP. Now let's say for oxygen gas, which has a molar mass of 32 grams per mole. And at STP, keep in mind, 1 mole of gas occupies a volume of 22.4 liters. And density is mass over volume. So in chemistry, the units of gas density is typically grams per liter. If you take the molar mass of oxygen, and if you divide it by 22.4 liters, notice that the moles cancel. And so you're going to get grams over liters. And this is going to be the density. So at STP, you can get another equation. At STP, the density of a gas is equal to the molar mass of that gas divided by 22.4. And if you need to find a molar mass, the molar mass of the gas is density times 22.4. Only at STP, standard temperature and pressure. And so this concludes all the equations that I want to go over in this video. And so I hope this video has been useful to you, and Thanks for watching and have a great day.